Hello and welcome to part 2 of lecture 26, where we're going to continue to talk about elasticity, stress and strain, but we're going to do some examples, having introduced the key terms and equations. So in example 1, we're looking at a kind of a typical extension problem. This is elasticity of extension. In this case, it is a piece of paracord that is getting extended. So the stuff that they make parachutes out of. All right, so a length of paracord is not to exceed 400 kilograms in terms of its total loaded mass when being used for parachuting. If the maximum upward acceleration of the person parachuting is 7.8 meters per second squared, then what must be the diameter of the paracord? Okay, so this is how we know it's going to be a stress and strain type of problem, is because we're given the cross-sectional area of the cord, and then we're going to relate that to some property, the material property of the paracord, using the equation of the elastic modulus. Okay, we're to assume a tensile strength of 500 times 10 to the 6 newtons per square meter. Okay, so that is our Young's modulus or elastic modulus right there. And that would be either you'd be told the exact material and look it up in a table, or in this case, you're just given it. And we're also given a safety factor. Okay. So why a safety factor? Well, this is another thing that you'll see in some problems. It would be specified, if I put in an exam, exactly what is meant by the safety factor, but this is it here. So safety factor is kind of a key term in itself that says that maximum stress, okay, so that's stress as in newtons per square meter, is ultimate strength divided by the safety factor. So maximum stress is something less than ultimate strength. And the idea is you don't want to actually design things to really be operating at their ultimate strength, but instead at some division, some fraction, I should say, some fraction of that ultimate strength. In this case, you're dividing by 7.5. So it's a big amount, right? You don't want to even come close to the ultimate strength. All right? So here is our free body diagram. This is the parachute up here. All right, we're defining positive y as upwards. The forces that are at play acting on the parachuter are the tension force and the gravitational force. So I've treated our stick figure here as the free body. Okay, so let's think about our net forces acting on the parachuter. So there would be tension in the positive direction minus gravity, and that would equal mass times acceleration. And this is the maximum acceleration, all right? And we're told here that the maximum upward acceleration is going to be 7.8. So A is something that we know. And also, obviously, it's correct to write MA, not negative MA, because the parachuter is accelerating upwards. That just means they're slowing down, right? Because before their parachute opened, they would have been accelerating downwards. Now that they're slowing down to some much lower terminal velocity than they would have without the parachute, their acceleration points up. Makes sense, okay? All right, so then that allows us to solve for the tension force. The upward acceleration makes the tension force bigger than it would be otherwise. That also makes sense. Okay, and so the tension that's going to show up in the paracord is then just going to be the mass of the parachuter times G plus A. Okay, A max. All right, so now we need to relate this to the stress formula, or the elastic modulus formula. So we're going to take that force and divide it by the cross-sectional area of the cord. Okay, so right here, this has the units of stress, and we're going to relate that maximum stress to the ultimate strength, which also has units of stress, or newtons per square meter, divided by the coefficient of the safety factor. Okay, and so now we'll plug in what we know. So we know that the tension force is based off of this right here, okay, and that's with the maximum rated upward acceleration, okay, and then the cross-sectional area is going to be pi r squared. We're then going to put in the ultimate strength that we were given of 500 times 10 to the 6, okay. And this is not the, this would be a different quantity and probably a harder one to look up, because this isn't the Young's modulus of paracord. This is actually the ultimate strength, which is quite a bit bigger than the Young's modulus. Because remember, Young's modulus is just the slope, okay? The ultimate strength is actually the y value. The reason that the slope and the y value have the same units is because the horizontal axis, the stress axis, is actually dimensionless. All right, so this is our equation. Hopefully it makes sense. Again, we're just kind of fitting our numbers into the definition of safety factor and its relation to maximum stress and ultimate strength. All right, so let's go ahead and solve for R. Okay, so here then I'm solving for R. I leave it symbolic so you can kind of see what it would look like to solve for R in a similar problem. Then I plug in the values here, safety factor, ultimate strength, the maximum load, because we were told that the load that the paracord is rated at is 400 kilograms. All right, the total acceleration, that's a plus g, and then pi. All right, and that gives us 5.8 millimeters. And since we were asked for the diameter, let's say thus, not thud, the diameter, of course, is just twice the radius, or 1.16 centimeters. All right, so you need a pretty thick piece of paracord. But this is also a very generous safety factor. Okay, all right, so hopefully all makes sense. So this is, again, a very typical example of a problem that involves the elastic modulus. All right, so let's look at one that involves another of the three moduli, this one being the bulk modulus. All right, so let's run through example 2 as well. A cube with 2 centimeter sides is made of material with a bulk modulus of 4.7 times 10 to the 5th. Okay, and this should say 10 to the 5th. You can see here that I tried to make the subscript, but I guess I didn't erase the 5 properly, but it should say 10 to the 5th. Okay, and the units, of course, newtons per square meter. When it is subjected to a pressure of 2 times 10 to the 5th pascals, the length of any of its sides is what? Okay, so before it was 2 centimeters to the side, but once it gets compressed, it should of course be smaller. The volume should be smaller, and then we should be able to find the new side length by relating the side length to a volume for a cube, right? Which is a pretty straightforward relationship. And this could be a problem that could be combined with fluids. If you wanted to be given, say, the hydrostatic depth of a material of water, for example, you could find out the depth in the ocean that would correspond to this pressure, and then from there, then you could find out the change in volume and so on. But in this case, since we're not doing anything with hydrostatics, we're instead just given the pressure. Okay, so let's find the initial volume. So V naught is just 2 centimeters cubed, which is 8 centimeters cubed. If we want to convert that to square meters, and I want to go ahead and convert this to square meters because our bulk modulus is given in terms of meters, right? So I decided to go ahead and convert the volume over. The important thing to remember is there's 1 million cubic centimeters per cubic meter. So if I want to convert from 8 cubic centimeters to cubic meters, I'm just going to divide by 1,000,000. Okay. Here I have my formula for bulk modulus, okay, from the key formulas. And so then I just want to solve for V final. So if you think about what V final is going to be, well, V final is going to be V naught minus the pressure times the initial volume divided by the bulk modulus. Okay. Well, where do I get that from? Well, I simply get that by rewriting delta V as V final minus V initial. Simple as that. Okay. And then I just solve for V final. Okay. And the negative persists. Okay, so then we got our initial volume. Here we're going to plug in the values that we know. So we know that we're given the pressure, we're given the initial volume. So we could have really factored out the initial volume. It had to be 1 minus, but for some reason I didn't. And then we divide by our bulk modulus, which is given for this particular material, which we're not told what it is. It's just some ambiguous material. Okay, so there it is. There is our final volume. But we weren't asked for the final volume. We were asked for the final side length. So we need to go ahead and take the cube root of that. And that gives us 0.17 meters. Of course, it's a much larger number, right? Because you're taking a cube root of a very small number, which gives you a larger number, or 1.7 centimeters. Well, there you have it. Each side went from a length of 2 centimeters down to 1.7. Got a neat result. Okay, so again, this would be very typical of a bulk modulus problem, especially this extra step of having to relate volume to side length. Could it be for some other shape? Yeah, maybe like a circular cylinder or something along those lines, but nothing too complicated. A cube being a great example. Okay, all right, so I got a couple more examples I want to show you. First of all, I don't want to show you examples 3 and 4 because I want to leave those for practice. Example 3 is going to be similar enough to example 6, which I am going to go over in just a moment. And example 4 is kind of similar to example 1, so it's going to be a good one for you to practice. But I did want to quickly go over example 5 because it's all about interpreting a stress-strain graph, and I think it'd be good to get some practice with that. So if we look here, in example 5, we're told that the figure shows the stress-strain curve for a material. The scale of the stress axis is set by S equals 300 in units of 10 to the 6 newtons per square meter. Okay, so that's in millions of newtons per square meter. What are A, the Young's modulus, okay, that should be the slope of the linear portion of the graph. B, the approximate yield strength for this material, that's when it changes from linear to nonlinear. And the approximate ultimate strength, and the approximate toughness. All right, so let's run through it. So E, the slope, should just be the rise or the run of the linear part. So I'm going to approximate that as a rise of 150, okay? And so what I'm going to go ahead, I'm going to be taking this part here. So if I look right, because if this is 300, which I think is 6, right? 1, 2, 3, 4, 5, 6. Yeah, so then 3 right here. The nice thing about choosing 3 is it intercepts exactly at a known value of 0.02. And so since it's linear, I can choose really any section of rise or run. So I choose this section here, okay? Instead of, say, trying to find, this point, which would be harder to find, okay? So hopefully that seems like a good choice to choose that intercept. So again, that point corresponds to 150. This point here corresponds to 0.02. All right, no units on the horizontal axis. My units are all cleared up on the vertical axis. And then I end up with an elastic modulus, or Young's modulus, of 7.5 times 10 to the 10 newtons per square meter. Looks good. All right, point B is the point where the linear slope ends. So we could approximate that as about 275. And again, that's saying that if S is 300, and then we know this is 150, so then we know each step is 50. So it's kind of halfway between the 250 and the 300 million newtons per square meter, where we kind of have the point where it stops being linear, right about there. And that's about 275. We see that the ultimate strength is about the same as the yield strength. And that again, I mean, I wouldn't so much say that, especially that we're working here. I think I was thinking the rupture. So the rupture strength, we could draw a straight line across, okay? But the ultimate strength actually would be much closer to 300. So I should really say that it actually is more about 300 instead of 275, because it's much, much closer to that value of S, okay? I'll fix that before I upload it. And lastly, toughness. Well, if you recall, toughness was the last key term I covered, and it's the area under the curve. And so the area under the curve is the toughness. So we have that each block has that area of about 50 times 10 to the 3 joules, right? So that's how much energy is in each of those blocks. So if we think of the area of the triangle, okay, so it's approximately a triangle. Obviously, it's kind of rounded on the top, but approximately a triangle. So the area of a triangle is given by 1/2 base times height. Let's take 1/2 times 0.45, because I'm kind of ending the triangle right there, times 300, again approximate. So I get about a total toughness of 6.75 times 10 to the 5 joules, or 675,000 joules. All right, looks great. That's how much energy you could put into the material before it broke. All right. So now finally, example 6. This is a bit of a longer example. All right, so this one is based on a biological phenomenon. A scallop forces open its shell with an elastic material called abductin, that is the actual name of it, whose Young's modulus is about 2.12 times 10 to the 5th newtons per meter. This piece of abductin is 5.15 millimeters long, and I'll show where that is in the figure, and has a cross-sectional area of 1.05 square centimeters. The abductin is compressed 3.34 millimeters, so it went from a length of 5.15 down to 3.34, so it got significantly compressed, right? It's like a pillar that you're pushing down, or like think compressing a spring, okay? And then when you release that compression, then it's going to spring open, okay? So we'll assume the shell is effectively composed of 2 plates, each with a moment of inertia of 1/3 ml squared. So essentially I'm taking this kind of curved section and treating it as a rough approximation as a rod, okay? And then I give you the mass of each of these plates and its length, okay? Like so. All right, and that's going to come up in part B. But first of all, part A. How much potential energy is stored in the compressed abductin? Okay, now this part, the part about finding how much potential energy there is stored in a compressed material, that's the part that is very similar to example 2 about the skyscraper. So, example 3. So if you want to look at the same approach and kind of get practice with that approach, make sure you understand it for working with the skyscraper problem, or just getting some practice. Look at the approach here, and then apply it to get that practice. All right, so here's the picture. This little green bit here is just showing that there's actually another muscle, and it's an active muscle that pulls the shell closed. The idea here, biologically speaking, is really fascinating. A lot of organisms have evolved these different biological materials. And so, you think about it, well, it's like, oh, well, if you're going to have to put energy into the muscle to store energy in the abductin, because that's what this kind of zigzag pattern looks like, that's the abductin, then it's going to take as much energy to, pull the muscle shut as it would to, spring the abductin open. Well, not necessarily, right? Because if the abductin has a very different elastic modulus than the muscle, then it's not as much energy. And that's actually the way a lot of organisms work, is the active muscle part has a different elastic modulus, less than the thing that's getting compressed. So you're actually storing more energy in there and then able to release it, okay? Now, it's not like you're getting energy from nowhere, but you're getting a greater acceleration than you would otherwise. So to say there's more energy is a misnomer. Let me rephrase. You're going to get a much faster acceleration because the much springier material will spring open quicker than the slower muscle was able to close it. So it's slow close, fast open. Okay, and that's actually really important for biological materials that need to kind of allow water to rush away, which creates the regions of low pressure, and then can refill their feeding tubes or whatever it may be. Okay, so and this is showing the quick spring away that the abductin allows. So what's the idea? What's the approach? So potential energy for elastic systems, we already have excuse me, we already have an equation for it, right? It's 1/2 kx squared, but we don't have a spring constant here. Right, so we need a new form of potential energy. Okay, didn't show up in the key equations, but definitely refer to this problem if you want to kind of think about what does potential energy look like for things other than springs. Well, let's see. Okay, so we make a substitution with Hooke's law. Okay, so we know that the K in our elastic potential energy that's specific to springs is based on Hooke's law, F equals Kx. Well, that means I could actually rewrite that Hooke's law to solve instead of for F, I could solve for K. Okay, that means then I could substitute K back into the potential energy and write it like this. And this would work for springs just fine. So this is the potential energy stored in a spring. 1/2 the force that you put into the spring times the displacement of the spring. But what's great about this formula is that it should apply to things other than springs. It should apply to materials in general, materials that have known Young's moduli. Okay? And so from the definition of the Young's modulus, this one right here, you can probably see we're going to make another substitution. We're going to get rid of that F in terms of solving this equation, the one that's in your key equations, for F. All right, so let's go down and take a look at that. All right, zoom out a tad. There we go. So here I've just took the definition of Young's modulus, solve for F. Then I'm going to substitute that into the potential energy equation that we rewrote from the spring version. Okay, so now it's looking quite a bit different now, right? So instead of it being 1/2 kx squared or 1/2 fx, and again, the reason it was fx is because the x in the denominator canceled with one of the x squareds in the numerator. But then we're going to have, we still the 1/2. Okay, our force became EA, delta L over L naught times delta L. Well, where are all the delta L's coming from? Well, because they're the x's, okay? Because if we solve this equation, the x can't be another variable. It is the change, right? That's what x always was in Hooke's law. It was the change in length of the spring. Well, in our new kind of version of Hooke's law, we always represent x as delta L for clarity, all right? So there we have it. So now I should just be able to plug in the numbers, and I do, right? So I plug in the elastic modulus that we were given, the specific one for the biological material of abductin. We plug in the cross-sectional area, again given. We plug in the change in length and the original length. We make sure to square the change in length. And we get 2.41 times 10 to the negative 2 joules, or 24.1 millijoules. Not a lot of energy, but it's a small organism. Okay. So in part B, we're asked, what is the angular speed of each shell after the abductin is completely released? Okay. So from conservation of energy, we're going to have the potential energy the elastic potential energy is going to have to equal the rotational kinetic energy, because in the absence of drag, and of course if this is an underwater organism, the drag would probably be pretty substantial, but if we ignore drag, all of the mechanical potential energy stored in the material, stored in the elastic material, would have to become kinetic energy. And in this case, nothing's translating, everything's pivoting about the hinge, so it's going to be entirely rotational kinetic energy. All right, so this is what it would look like. Our elastic potential energy would become rotational kinetic with the form of 1/2 I omega squared, the familiar form of rotational kinetic energy. Okay, and so then I'm just going to put in our moment of inertia. Notice I have a 2, that's because there's 2 shells. So the total moment of inertia is the sum of each shell. All right, and then I solve for omega. All right, so I just set it up, simplified it, cleaned it up a bit, plug in all the numbers, and we get 55.1 radians per second. Okay? So that's how fast it flies open. Now I actually don't have a part C here, but I think I must have been a previous version. I just want to show that if we were to find the translational velocity of the tip, then that would just be omega times L, and it ends up being 2.42 meters per second, about 5 miles per hour. So it's fast, right? It's like springing open quite quickly. All right, so hopefully these problems exploring, in this case, elastic potential energy for a material, or typical problems of bulk modulus and Young's modulus, help give you an idea of what elasticity problems look like and help you understand what a stress strain curve is all about. And thank you for watching.